Hello Internet, I'm Early and this is Coding Hacks. Today we're going to introduce a new series that I'm doing, which is to implement this book, which is Computer Programs for Structural Analysis by William Weaver. It's a 1967 computer programming book, and we'll be working to get through page 8 of that book today, which sounds like not a lot of detail, but trust me, it is a dense book. So I am not a structural engineer. I'm actually a computer programmer by training. I've got more years of experience than I care to admit, but I've been doing this particular book since around 1997. We never actually did the whole book. We only got through what's called a plane frame, which means that the structures that we were analyzing were considered to be two-dimensional only. The reason for that was that we were more in the business of selling a particular product that was itself mostly just two-dimensional. So in order to make sure that my time wasn't spent on things that company didn't need, we never bothered going beyond the plane frame side of things. And most of the work that I did at that company involved checking building codes to make sure that the structures that we were analyzing met the building code and keeping up with what the building codes had done. Things like checking to make sure that the metal plates on the structures that held the members together were up to code. From New Orleans, in case you can't tell from the t-shirt and the fleur-de-lis thermos. Amazingly, I'm from New Orleans, but that is not an alcoholic beverage. I'll save that for later. Let's talk a little bit about this book and how it works. The program that they introduce uses something called the stiffness method of structural analysis. And what that does is it says that every structure is made up of what are called prismatic members. And a prismatic member is just an object that has a cross-section and a length. So for example, this pencil between my two fingers has a circular cross-section and a length. Now this is not a prismatic member because that cross-section varies over the length. So over here we have these little nubs that bounce up and down, and then back here there's an insert that comes out, and that is a different or would be considered a different member in the structure. So obviously, we're not going to be analyzing pencils. We're talking about things made out of 2x4s and 2x6s or steel. And the important thing is that the cross-section and the material properties stay the same for the length of a member. Anywhere those change, you have to have what's called a node, which is just a structural analysis way of saying this is where two members connect to one another. Once we know what a member is and what a node is, we can talk about what properties those different objects have. So a member, like I said, has a cross-section and a material, and it also has two nodes that it connects to. And those nodes have coordinates and what are called degrees of freedom. So if you think about a position in space and members framing into it, if I apply a force, that node is going to move. And so the degrees of freedom refers to what directions or in what manner that node can move under load. When we talk about loads, we're talking about literally just forces being applied to something or twisting being applied to something. A node can move under load, so it can displace or it can rotate in space. And when you move in space, that's called translation, and that can happen we're using the Cartesian coordinate system, so that can happen in X, Y, or Z. And rotation can happen in directions parallel to those axes. So it can rotate about the x-axis, about the y-axis, or about the y-axis, or about the z-axis. In this book, we adopt the Cartesian coordinate system, and the right-hand rule as to how the axes are represented to each other. So if we start like this and we say that this is the x-axis, we bend our fingers towards the y-axis, then z will be pointing in that direction. So if we want z to point towards the camera, then that means that the y-axis has to point down if the x-axis is pointing off to your left. And if we have it pointing off to my right and y pointing up, which is kind of how most people tend to think about this, then the z-axis will be pointing away from the camera or back towards me. So we've talked about the coordinate system, nodes, members, displacements, and the fact that members have cross sections and material properties. So let's talk about what those actually are for a minute. So a cross section is just a discussion of what you would see if you just took a member and sliced right through it. So if you think about a piece of wood, a 2x4, we call them in the United States, is a piece of wood that is 1.5 inches by 3.5 inches, because just like everything else in the imperial system, we can't have it make any sense. Why on earth is it called a 2x4 when it's not 2 inches by 4 inches? The answer is because we're also a greedy capitalistic society, and they leave out 1/2 inch in each direction. Now it's because we cut them at 2 inches and then we put them in a kiln and they shrink down to 1.5 inches. So 1.5 inches by 3.5 is a rectangular cross section. You could also have a pipe that has a circular cross section with a hollow section in the middle as a structural member. Very common to use pipes for columns. You can also have a steel beam, which will often have a cross section shaped like the letter I, a capital I. We often call those I-beams, but they are more properly called a wide flange beam because the flanges that come off at the top and bottom are very wide, and that produces significant strength for the beam. There's basically any number, like if you can imagine a cross section, you could conceivably make a prismatic member out of it. So there's a lot of aluminum extrusions that have channels on each of the faces so that you can bolt things into it, and those are prismatic members because they have that constant cross section. So once we're done talking about the geometric properties, it's time to move on to the material properties, which refers to what the member is made of, and more specifically the characteristics of that material. So a material can mean a type of wood, so oak or pine, a type of metal like steel or titanium or aluminum. And then the properties that we're interested in are not just what it's made of, but what the strength of that particular material is. So steel has a very high tensile strength and compressive strength. Concrete, as another example, has an extremely high compressive strength but doesn't do as well in tension. We have wood, which is fairly balanced between tension and compression, but obviously much weaker than either steel or concrete. And so there are actually tables available that tell you the actual values and numbers that you can assign to each of those different materials. And so part of what we'll be doing in this analysis is building up a database of those materials, and we'll talk through these specifics as we go. So with the stiffness method of analysis, what we're talking about is describing all of these objects using matrices. So we'll be doing some linear algebra and constructing those matrices in such a way that we represent the cross sections, the nodes, the material properties, and then we just do some matrix multiplication, and we find out, based on some structural engineering equations, what the displacements of those nodes will be. And that's really what we're after from this book, is if I have a structure and I have these forces, how do those nodes displace? And at that, we'll go ahead and jump to the computer. Now we are going to move on to talking about the 6 types of structures covered in the Weaver book. And here we go. So the 6 are the beam, plane truss, plane frame, grid, the space truss, and we have the space frame. All right, so let's talk about each of these in turn. The beam. Generally speaking, a beam is a collinear set of members. So we could have a node here, and we could have support, maybe a roller here, maybe a roller here, and maybe a roller here. So these symbols that I've drawn under this member or this set of members are how structural engineers describe the restraints placed on the system. So in this case, we have on this left end here, we have a pin, which means that it won't let the node move in X or Y. However, it will allow the member to rotate at that point. That's one type of restraint that you could have. Another is the roller, which prevents movement up or down, but allows horizontal movement. And generally speaking, that's the 2 types of supports that are kind of most commonly used. You could also have what's called a fixed support, which is usually drawn something like that. And that just means that, this member is fully supported at that end. It can't move side to side, so that's not allowed. It can't move up or down, so that's not allowed. And it cannot rotate at all, so that's not allowed. Yeah, so those are the different types of supports. So a beam structure can have concentrated loads applied to it in the form of like a vertical load, or maybe there's uh, something pulling on it sideways, or you could have something trying to twist or bend that beam. Now, if we look at it, obviously we're analyzing it here in effectively 2 dimensions, but in reality, any beam is going to be a 3-dimensional object. And that pin, might, if it were a real thing, might actually, come through the structure and be held up. And, your forces kind of come down into the structure like this. And what differentiates a beam from some other type of structure is that, twisting that you're applying has to be in the same plane as the beam. So and same thing with forces, right? So we can have something pulling on the beam, through the length of the beam. But what we can't do is have something pressing against the side of the beam. The most we can do in that orientation would be to have something grabbing the beam and trying to bend it like that. Oh, there's another type of force. So this is a concentrated force. This is a concentrated force or a point force. You can also have what are called distributed forces. They could look like that, where you can think of this as like I've got something on top of this that is long and heavy, and that doesn't necessarily have to be, something that is equally heavy across its whole length. It could be very light on one end and heavy on the other. And you can have all kinds of different shapes of forces as well. But for a beam, the important thing is that they are all forces are in the same plane as the beam, and any twisting is about an axis perpendicular to the beam, and perpendicular to the whole system, so that it effectively is, if you draw it this way up here, that any twisting applied to it is the axis of the twisting is perpendicular to this whole system. So you can't have something trying to twist it this way. Only that way. So now let's move on and talk about plane trusses. So a truss is a structure where it has multiple members and they are connected at nodes that do not transfer any bending. So you can think of this as like very common examples are like train bridges um, from olden days would have a series of nodes like this, and they might have a series of nodes like this and members that do something like this. And they might have a pin at one end and then a roller at the other end, but each of these individual nodes does not transfer any bending. So if there's a force right here, then what that means is over here, the only thing that this member can see as a result of this force is that this node is trying to move in that direction because this force is effectively pulling, and it's probably also moving in that direction, is pulling on this member. And so that will put this member over here into what's called tension. So you can think of that member as being either squeezed or pulled, like trying to pull apart. And so this member will be stretching because this one is pulling on that member. So just like with a beam, we can have forces applied at inside members or at nodes. We can have both horizontal and vertical forces. And we can have twisting applied, but the twisting has to be oriented about effectively the z-axis so that we are keeping everything that happens in the structure in the same plane as the structure. And that means that this structure is two-dimensional, just like a beam. So, and that was a plane truss. So one thing that I need to bring up very quickly about plane trusses is that the only types of supports allowed are pins and rollers. So in a plane truss, you cannot have fixed supports. And that again is because the idealization of the structure is that all of the or rather none of the nodes will transfer or resist twisting. So the book refers to this as having hinged joints. So next we have the plane frame, which is similar to a plane truss, except that we can have rigid joints and therefore bending here can transfer. The big difference with a plane frame is that now we allow fixed supports. So we could put something here and say, you know what, that force can't, or that node can't rotate. Or we can say, hey, this node is not hinged and allows for this twist to affect this member over here. So this member might, instead of being just in tension or compression, it may have some bend to it because of this applied twisting. And the structural term for the twisting, by the way, is a moment. So this is the type of structure that I spent a lot of time writing code supporting, and we would figure out the joint displacements and then backtrack from that to figure out the displacement at each point along a member in order to figure out the stresses inside of those members and determine whether or not the material was strong enough to handle that. So next, we will talk about grids. So we'll just clear this and we'll say grid. And for a grid, you can kind of think of this as similar to a plane frame, except that the forces and applied moments are in the opposite or in an orthogonal direction. So in a plane frame, we might have, these members, and all of the forces have to be applied inside the plane that the frame exists in. So if we were to draw this in 3 dimensions, right, we might have 2 by 4 like this, and it might, you know, frame into another 2 by 4, and we'll just kind of draw it like that. And we'll, instead of the one that I just drew, we'll do this as effectively like an A-frame sort of a structure. And the forces could only be applied inside the same plane. So a force coming into the structure like that is not allowed. So with a grid, so these are plane frames. With a grid, you can think of it as a series of members that are next to each other. And one way to kind of think about this is a good example of a grid in real life would be the framing for a floor, right? So you might have some with like traditional 2 by 12s or something. So you might have a series of 2 by 12s laid out literally in a grid, right? And when you think of a floor, the forces on a floor, with the exception like of an earthquake, are really, people standing on the floor or bookshelves or, things like that, walls from above. And so all the forces are applied perpendicular to the plane of the structure. And twisting for a grid has to be applied not like that, but like that as well. And so what that means is grids and plane frames are basically the same thing, except that forces are applied orthogonally in a grid. Those are all of the two-dimensional things, right? So we have beam, plane truss, plane frame, and grid. And these are all 2D structures with effectively 3D forces because the twisting moments are orthogonal to the structure, or they are, or the forces themselves are orthogonal to the structure. So next we'll talk about the 3D structure types. So I mentioned them at the top of this. We've got a space truss, and that just means that we've got nodes kind of three-dimensionally. So we can imagine like a tetrahedron, right? The difference here is that now instead of the z coordinate for each of the nodes being 0, we've got one out here that's, not at 0. And then forces can be kind of any which direction, and our moments can also be in any direction, and we kind of start drawing them as double-headed arrows. And we can have, I believe for a space truss, the hinged connection part stays true, and we cannot, transfer bending from one member to the next. And so that means that we can only have pins and rollers for supports as well. But those pins and rollers can prevent rotation, or not rotation, they can prevent translation in any of the dimensions. So X, Y, or Z. Okay, so that is space truss, right? So now we'll talk about the most general type of structure that's covered in this book, which is the space frame. And the difference now is, again, we can make it so that bending can transfer through nodes, and we can make it so that restraints will prevent bending as well. And so that becomes the differentiating factor that makes something a space frame instead of a space truss. And obviously, the more degrees of freedom that you allow and the more complexity you allow in terms of whether or not bending can make it through a node, makes it where the analysis becomes more and more complicated as you progress through these 6 types of structures. And on the next video, we will talk about the stiffness method, which is the linear algebra approach to actually figuring out how much these nodes bend based on the geometry and material properties and forces of the structure. So thank you very much for joining me on this first video, and I will see you on the next one. Please like, comment, and subscribe. And now it's time for bloopers. Hello, Internet. I feel so stupid.
You gotta get comfortable. Okay, 2.
Yep.
All right.
Hello, Internet. I'm Early, and this is Coding Hacks. I'd like to. I said
Oh.
You could have a wide flange steel beam, and those are sometimes called I-beams, or I can't remember what Colin First calls it. Dang it. We'll have to do some jump cutting here. You can also have a steel, or it could refer to a type of metal like wood or steel, or wood or steel. We'll cut. That was close to good, but I ran out of. I started to hallucinate.
Hold on.
Like an LLM.